An underdamped second order system is one in which, when having a new input or step input go into the system, we're going to see some oscillation until we hit our new equilibrium. And because of that, we can describe what's going on with some key equations. But one thing I want to stress is that we can only use these equations, and let's use some red to specify, when we have an underdamped second order system. So when is it an underdamped second order system? It's going to be when zeta is greater than 0 and less than 1. And so zeta will be greater than 0 and less than 1. And here we have a transfer function, and for this handout, it says that we just have a standard. This is a second order system where we do not have an a value. Oops, let's go back. Where we do not have an a value. So we can just put an a value there and then say that this could be a times b. And here we have 90% of a times b and 0.1% of a times b, where our input is b over s. So it's a unit step with, a step function with input b as opposed to just a unit step. But for the numbers here, we're saying that a and b are equal to 1. But I'm just going to have everything in terms of a and b, so we have a little bit more flexibility when using this. So when we talk about what's going on in our system, we can start to see that we have a system that will oscillate, and we have a peak here. And the peak occurs at Tp, which is the peak time. And there is a percent overshoot, MP, which lets us know how far we go past our peak value. And so we can call this our peak. We can also call it our overshoot. If we want to think of how quickly we are getting to our equilibrium point, or how quickly we're getting to our final value, we can look at something called our rise time. Let's use a different color. Let's go with green. So the rise time is going to tell us how quickly we go from 10% of our final value to 90%. So we can see we start off at 10% and we end at 90%, and the amount of time that takes is considered to be our rise time. Then we've talked about settling time before, when we had our first order functions. So the settling time tells us how long it takes to get within plus or minus a given percentage of steady state. So that lets us know when we can start to take accurate readings, if we have a measurement system that oscillates like a scale, or how long it is till we can expect that our change is negligible, depending on what percentage we have. For any second order underdamped system, our output, so this curve here, can be defined as y is equal to AB times 1 minus e to the negative zeta omega nt, which reminds us a little bit of our first order functions. But now we're going to multiply by cosine omega dt plus beta sine omega dt. So that damped natural frequency where omega d is equal to omega n times the square root of 1 minus zeta squared. And this number will always be real so long as zeta is less than 0 and as between 0 and 1. If zeta is greater than that, you're going to get an imaginary number within your damped natural frequency, which means you did not follow that rule in red up here that says only use if zeta is between 0 and negative 1. And so that is our damped natural frequency, or our damped frequency. So for our overshoot, we can say a couple of things that are happening here. So one is the peak time. We can say that this peak time, TP, is equal to pi over our omega d. This is a rule of thumb. So the equations that I'm giving here are not the exact scenario, but it's tools that we're going to use to get a provided estimate. So I'll have that overshoot is equal to our peak time, so the time where overshoot has its maximum value, roughly occurs at pi over omega n 1 minus zeta squared. We have that our mass, our percent overshoot, MP, will be equal to either, if we want to find it from a graph, we can say 100% times our peak value minus steady state over our steady state value. Or if we want to predict it ahead of time based off of our transfer function, we can say that it will be 100% times, and this will be the exponent, so e to the power, but just to make it a little bit easier to see, of negative pi zeta over the square root of 1 minus zeta squared. So we are taking our equation and we're just plugging in when time is equal to our peak time. That all looks good to me. Then finally we have our rise time and settling time. Don't know why I say finally when we have two things. But our rise time, this one is really just an estimate. So I know that Dr. Sinai uses a different rise time, and I've seen this is one that Dr. Wu uses. This is just a rule of thumb if you want to do some control theory and you just want to have an idea. But we're going to use 1.8 over omega n, and we could also, or we could say that it's equal to, for Dr. Sinai's class, he says 2.16 zeta plus 0.6 over omega n. Whichever one you want to use is fine. On homeworks, I'll let you know. I'll let you know which one to use, or just use either of them. But the second one is accurate as long as if zeta is between 0.3 and 0.8. And now our settling time is going to be based off of what percent we want to go to. So if we want to have a 2% settling time, so when we're within plus or minus 2% of our steady state, that's going to be 4 over zeta omega n. If we want to have a settling time of 5%, that's going to be 3 over zeta omega n. So if this looks familiar, then that is because we've seen this before. Because we've had this where we had our settling time for that we were at 98%, so within 2% of our final answer was 4 tau. If we want to be within 5%, it would be 3 tau. So we can say that the tau of a second order system is equal to 1 over zeta omega n. And these are the equations we can use to describe what's going on in an underdamped second order system. So we will have some homeworks with them. We're going to figure out how we're going to do the Lego labs or a version of the Lego labs, but these are ways that we can go through these options.